Hello, welcome back to Algebra. Here we're going to cover the very important concept called point-slope form of the equation of a line. I know it's a big mouthful. But the bottom line is, if you remember where we've been, we talked about the equation of a line in standard form. We can graph it, but it's kind of a pain because we have to find 2 points on the line and we have to do it manually and draw the line. But then we introduced the concept of slope-intercept form, which is mx plus b, right? That one was great because all we could do is then pull the y-intercept off the equation and then pull the slope off the equation, and we don't have to really find any other points. We just put them on there and then immediately graph the lines. Great. Okay, so the point is if I asked you to write an equation of a line and I give you the slope and I give you the y-intercept, it's really easy. It's just mx plus b. But what if I don't give you the slope and the y-intercept? What if I give you the slope and just any other point on the line, right? So you know the slope is going to dictate how the line looks, how slanted it is. And if I give you another point on the line, it should be enough to define what the line looks like, but how would I write the equation of a line from that? If I just gave you the slope of the line and then any other point on the line, not just the y-intercept, but any point anywhere, it turns out that there's an equation that's very handy to do that. It's called the point-slope form. That's why it's called that, because in order to use it, you have to know a point on the line, any point, doesn't have to be an intercept, anywhere on the line, and you need to know the slope of the line. So what I want to do is I want to show you what that equation is, and then I want to show you where it comes from, and then we're going to solve a couple of quick problems to show you how to use it, right? So we're going to talk about what it is, where it comes from, and also how to use it. And so to do that, let's go down memory lane where we talked about the following. Recall that we have a couple of different equations of lines now that we've already talked about. We have standard form, ax plus by is equal to c. This is called standard form. I'll put that over here to remind you, standard form. But we also had, and that was, that's the real form of the line, but it's also not terribly handy to graph things with. So we actually, when we solve this thing for y, you end up with y is equal to mx plus b, which is really handy. This one's called slope-intercept form. And the reason why it's handy is because you can read the slope and the y-intercept directly off of the graph. So let me go the other way. In order to write this equation in this form, what do you need? You need to know the slope and you need to know the y-intercept. If I give you the slope and I give you the y-intercept, you can immediately plug it in there and you can tell me mx plus b, and it gives you the equation of a line, and there you go. Well, there's a third version of the equation of a line that comes from, just like this one came from this one, I showed you how to do that before, there's another equation of a line that's called the following. It's called the point slope form. I'm not going to write it all out, but it's the point-slope form of the equation of a line. I'm not going to write that whole thing out, but it's called the point-slope form. Here's how it looks. Y minus y1 is equal to m times x minus x1. This is it in all of its glory, and basically this means that the m is the slope, just like it always is in all of these equations. And the point, notice we have some y1 and x1 here. The point x1 comma y1 is just any point on the line. It does not have to be an intercept of any kind. Any point, anywhere, even way over there. As long as it's on the line, I can use it and I can stick these values in here. I can stick the slope in and I'll have an equation of a line that I can then go plot. So, just like for the slope-intercept form, in order to write the equation, I needed the slope and I need the y-intercept. In order to use this form, I need to know the slope and I need to know any other point on the line. Now you might ask, why do we have so many different forms of the same thing, which is just an equation of a line? 2 reasons. Number 1, because as I mentioned about 37 times already, lines are really important. They're used to solve tons of real problems in science and math and engineering. Trust me, when we get to chemistry, when you get to physics, lots of equations will just look like a line. Lots of them. All right, I can go on and on about that. But the other reason is because a lot of times in real problems, you know different things about whatever it is you're studying. So if you happen to know the slope and the y-intercept, then I would just go ahead and use this equation of the line because it's what I know. I can just write it down, mx plus b. But maybe I don't know the slope and the y-intercept. Maybe I know the slope and some other point on the line, but it's not an intercept, it's just some other point. Well, then I would use this equation of the line because it's what I know, it's what I have from my data in my lab or whatever I've done, and then I can plug it into here and I can graph it because I know this. So the answer to the question is, why do we have so many different equations for lines? Well, the reason is because in real life, I might know the slope and the y-intercept, so I'd use that one, or I might know the slope and some other point, and then I would use this one. So it depends on what you know as to which one you use. So what I could do, if I wanted to, is I could just stop here and say, hey guys, this is really important. Let's go solve a bunch of problems and then move on. And just tell you, trust me, this is called the point-slope form of a line. And you guys would do that. I mean, of course you would. You would say, great, let's use it. But I want to take 5 minutes to show you where that equation comes from, because it looks really weird and it looks like it doesn't belong as an equation of a line. So I want to talk a little bit about where it comes from, and to show you that it's not black magic, and then after that we're going to solve some quick problems to show you how to use it. So it'll be very simple. It's not hard at all. So what we're saying is that to use this equation, we have to know a point on the line, x1, y1. Right? And also notice there's an x and a y running around here too. So we can kind of think of it as 2 points. I want to go ahead and plot over here 2 points on this graph. I don't really care what they are, so I'm going to pick this point right here, and I'll pick, like, I don't know, let's do this point right here. So what I'm going to do is I'm going to draw a line through these 2 points before we go any farther. Right? So here's a line, any 2 points. I picked them at random because it doesn't honestly matter. Right? So there we go. There's a line. And I can put a little arrow here and here if I want to. It doesn't matter. All right, so what do I know? I know that this point, right, I can read it. It's 3, 2. But in general, I don't care what the line looks like, so I'm not going to label it 3, 2. I'm going to label it generally as, well, I think probably the better way to do it is to show down here, this is, the x value is x1, and the y value is y1. Do you see? Because the value of this point is what? x1, y1, right? So let me go ahead and draw, probably to make it clear, let me draw a little arrow here. The value of this point on this line is x1, y1. This is the same x1 and y1 that we're going to end up using in the equation itself. But for now, just say, hey, there's a line, there's a point. It's got an x value, it's got a y value. So I'm going to call it x1, y1. Okay, you're with me so far. Now I have another point. What do you think I'm going to do with this one? Let's go down here and say, well, whatever this point is, it's going to have some x value. I'm going to call this x. I'm not going to call it x2, but I could call it x2. I'm just going to call it x. Notice that I don't put a number 1 here because I'm going to be able to. I want to be able to tell it apart from this one. This is just going to be called x, and this one over here is just going to be called y. Now I can read off the chart that this is 9 for x and this is like 4 for y, but it doesn't matter because this line could be pointed anywhere. I just have 2 points, x, y for 1 point, x1, y1 for another point. So just to make it absolutely clear, the value of this point is at x, y. Right? Now, what I want to do next is I want to go to another board and I want to ask you, or remind you, what is the equation of a line? Of course, you can write the equation of a line in standard form. But we already talked about the fact that we like this one better because it's easier to graph it. And this one here, the one that we've been using in the last section, it comes from the standard form. So these are basically the same thing. You just solve for y to get this one. So let's start by using the slope-intercept version because it's already solved for y. So the equation of any line can be written as y equals mx plus b, right? Anything. So this is a line, and this means that all points on this line have to satisfy that equation, mx plus b. So if I stick the value of x1 into that equation, it'll give me the value of y1 out. If I know of course, if I know the equation, if I know m and I know b and I know the equation of a line, I can put any value of x in, and it'll give me the value of y out. We've been doing that over and over again. So in general, I'm trying to keep it general here. Okay, so I'll say for point x, which remember point x is this one over here, for point x, the y value is the following. What do you think it is? It's going to be y equals mx plus b. I take the value of x, I stick it in here, multiply by the slope, whatever it is, add the y-intercept, whatever it is, out will come the value of y that corresponds to this x value. So if I know this x value, I stick it into the equation of a line, and out will come the value of y that corresponds to it. Now don't lose me here because I'm getting to the point really quickly, I promise. All right, so let's say for the other point on that line, for point x sub 1, the y sub 1 value is, what do you think it is? And remember, I take any point I want for x, I run it through the equation, I get the other guy. So what I'm telling you is that because it's on this equation, y sub 1 is going to be equal to the slope m times x sub 1 plus b. So far, literally we've done nothing. All I said is there's an equation of a line, it's mx plus b. And now I'm going to pick 2 points on this line. Here's one, here's one. I'm going to call this one x comma y, and I'm going to call this one x1 comma y1. Now, if I want to find out what the y value is that corresponds to this, I just run it through mx plus b. This is the y value that goes with that x. And if I want to know the y value here, I just run the x1 value through and it gives me y1. M times x1 plus b. That gives me the y1 value. So here's the punchline. Okay. What is the value y minus y1? In other words, I can calculate anything I want in math, right? So let's take a look over here, and let's say, here is the y1 value of this point, the y value of this point, this is the y value of this point. Let us find out what is the difference between these guys. What is y minus y1 equals, question mark. I want to calculate the vertical difference between these 2 points. I want to subtract y minus y1 because I want to find out how much higher this point is above this one. So I want to calculate what is y minus y1. So what do? I say, well, y minus y1 is what? Well, y I just said was this for the other point over here, mx plus b, because this is what y is for that point over there that I called y. But I'm going to subtract y1 from it. I'm going to find the vertical difference between it, so I have to subtract off the other value here, mx1 plus b, right? Y minus y1. This is exactly what I've written down here. So literally all I'm doing is I'm finding the distance between this vertical distance between this point and this point by subtracting the y values, but I know what they're equal to, so I subtract their equivalents. So what do I get? Y minus y1 equals, here's mx plus b. What do I do with this minus sign? I distribute it in minus mx1 minus b. But look at what happens. A beautiful thing happens because I'm going to add terms, but I have a b plus b, which is going to completely subtract with a minus b, giving me 0 for those 2 terms. So all I'm going to be left with is y minus y1 equals, here I have mx minus mx1. But notice I have a common m. So let me pull that out. Minus y1 equals m times what do I have in here? X minus x1. Y minus y1 is equal to m times x minus x1. Y minus y1 is equal to m times x minus x1. I only did that for you, not because you're going to be asked on a test, and not because it's particularly something you're going to use every day, but I did it just to show you that it doesn't come from nowhere, that it doesn't just get pulled out of a book and they say, here's another equation. Literally that equation comes from this version of the equation for a line, which is also comes from this one. So it's all just different ways of rewriting the same thing. I mean, you all know that the fraction 1/2, I can write the fraction 1/2 lots of different ways. I can write it as 1/2. I can write the fraction as 5/10. I can also write the fraction 1/2 as 3/6. I can write the fraction 1/2 as 4/8. It's lots of different ways to write the fraction 1/2. Just the same thing for lines. Here's a way to write a line, and this is also a way to write a line. It looks a little different, but it's still the equation of a line. And it turns out that this is another way to write a line. It looks a little different, but it's also an equation of a line. The exact same thing with the fraction analogy. So I use this one when I know the slope and the y-intercept, and I use this one when I know the slope and any other point on the line. And then I can plug it into this equation here. And where it comes from is by basically taking the y values of 2 different points on the line and subtracting them, and then you get some cancellations, and then here's the useful equation. Now, Why do we have it? We have it because it's useful. So let's go ahead and show how it's useful by giving you the following couple of quick problems. These are not going to be very difficult at all. But I'm going to give you the following information. What if I tell you the slope of a line is 1/2? All right? And the slope, the line also goes through a point, 1, 2. Notice that this is not a y-intercept. A y-intercept would be 0, something. This is not a y-intercept. It's just any point on the line, any point, right? But I have the slope, and I have the point, another point, any other point on the line. And I said write an equation of a line. You would not be able to use mx plus b because you know the mx part if you know the slope, but you don't know the y-intercept. I didn't give it to you. That point that's on that problem over there is not the y-intercept because the y-intercept is where it crosses the y-axis. This point is not anywhere near the y, well, I guess it's kind of near it, but it's not on the y-axis. So this is not a y-intercept. You can't use that for mx plus b. So what would you do? Well, you use what we learned today. So you would say, well, wait a minute, I know a slope and I know a point on the line. So I'm going to use the point slope form. Y minus y1 equals m times x minus x1. And I would say, well, y minus, notice that this guy, when they give you a point on the line, this is basically x1, y1. It's always the secondary guy here. This guy, these guys here, you leave them alone. For y1, it's equal to 2. Equals the slope of 1/2 times x. You leave this one alone, minus the other value here, which is x is equal to 1. So literally, we put it in there. Now, technically, this is actually an equation of the line. You could kind of circle it, but really nobody wants you to do that. We want you to simplify it. So the first thing you do is you say y minus 2 is equal to, you distribute the 1/2, making it 1/2 x. The minus sign has to come along for the ride. 1/2 times 1 gives you 1/2, right? Like this. And then you want to get y by itself, so you want to move the 2 over here. So what you're going to get is y equals 1/2 x minus 1/2 plus 2. Now, if you're really good with fractions in your mind, then you can add these numbers together. But a lot of people aren't, so we need to learn how to deal with the fractions. So what you have is negative 1/2 plus 2, which is the same thing as negative 1/2 plus 2 over 1. Now we need a common denominator. You can't do this without having a common denominator, right? So what I'm going to do is I need a common denominator. I'm going to choose a denominator of 2, which means I'm going to multiply the top of this fraction and the bottom of this fraction by 2 so that I can get a common denominator. So I'll have negative 1/2 plus, then I have 2 times 2 is 4 over 2. You should know that 4/2 is the same thing as 2 over 1, right? It's the same thing. And so what I'm going to have is, for the answer, I'm going to have a common denominator of 2, and now I have to have negative 1 plus 4. I just add the numerators, which is going to give me a positive 3. So I'm going to have 3 halves. Now, a lot of you probably could do this in your head, but I'm showing everything because if the fractions were harder, then you'd have to, add them up manually. So what we have is y equals 1/2 x, and then all of this stuff came out to positive 3 halves plus 3 halves. Now you see what you have is I've given you the slope and I've given you a point on the line, and you went all through this stuff and you got it into an mx plus b form. So if I asked you to circle the equation on the line, you would circle this because that is a valid equation of this line, and then you would go ahead and plot that guy. So what I'm going to do now is erase this, and we're going to plot this line to show what it looks like. Now you see we have the equation of this line given the information we have, and we can now read the slope immediately off as 1/2, and we can read the y-intercept immediately off as 3 halves. All right, so then we go over here and we say, well, the y-intercept is 3 halves, which, by the way, when you run this through a calculator, this is going to be about 1.5. It's going to be exactly 1.5. So if this is 1 and this is 2, then the y-intercept is right between them at 3 halves, as best I can do it. All right, and then from that point, we rise 1 and we run 1 to the right. So from here, we go up 1 and then over to the right 2. 1, 2. So this dot will be somewhere close to this. I mean, it's not going to be exact because, I'm not a computer, but it's pretty close. So there we have this guy here. We'll try to do our best to go, I'm trying to get it accurate because I want to point something out to you once I get it in place. So let's put that as the equation of the line. So here are some arrows like this. So we're saying that we can start with a slope and we can start with any point. We can run it through the point slope formula and out will come a familiar equation of the line mx plus b, which is easy to graph. So oftentimes what you'll do is you'll get it into slope-intercept form so you can graph it, which we pull the information off and we graphed it here. Now this line, we graphed it using this information down here from the equation we found. We're saying that this line goes through the point 1, 2. So now that we've graphed it, let's double check and see if it goes to the point 1, 2. Here's 1, 1, 2. Bingo, right there. It goes right through that line. X is equal to 1, y is equal to 2. And notice that this point, it is on the line, but it is not one of the points I used to graph the line. I used the y-intercept, which came from this form of the equation, with the slope here to go to find the next point, and 1, 2 just falls out because it's also on the line. All right, also on the line. All right, let's see, how much free space do I have? I think I don't have too much free space. Let me go ahead and just erase this a little bit, and I think I can fit everything in comfortably down here for our last problem. So for our last problem, I'm going to give you the following information. I'm going to tell you that the slope of this equation of a line is -2, and that it passes through a point 1, 1. And I'm going to ask you to write the equation of the line and graph it. The first thing you're going to try to do is say, well, I'm going to use mx plus b, right? I know the slope, but this is not a y-intercept. It doesn't go through the crossing of the y-axis. That's not what 1, 1 is. So you can't use mx plus b, so we're going to use the point slope form, which is what? It's y minus y1 equals m times x minus x1. And then I just put in the information. I say y minus y1 means this number 1 coming from the line, the point that it goes through, equals the slope of -2 times x minus the x point of the point that you have here. And then, to simplify further, I'm going to multiply the -2 in, giving me -2x. Multiply the -2 times -1 is going to give me a +2. And then finally, to get y by itself, I'm just going to add 1. Because adding 1 will kill it on the left, and on the right I'll have -2x, and then if I add 1 over here, I will get a +3. Right? So I now have, first of all, can circle this and say this is the equation of the line that I get from a value of a slope of -2 going through this point. Now how can I graph it easily? Well, from this I can immediately see that the y-intercept is just equal to 0, 3. That's where it crosses the y-axis. And from here the slope is equal to -2, which the better way to write it is -2 over 1, because you're going to have to do rise over run, right? So let's do that. Let's go ahead and figure out that where the y-intercept is up here at 0, 3, 1, 2, 3, which is right here. Now this is a little tricky because the slope is negative. That means usually you rise up and you go over, but since it's negative, I have to rise down and then go over. So rise down and then over, rise down 2. So 1, 2, and then over 1 unit to the right. Down 2, over 1 unit to the right. And then I'm going to go and do my best to draw a fairly straight line through these points because I want to show you something else once I get that done. So let me go ahead and try to make it as good as I can and draw a line that goes something like this. All right, so there's a line, goes on in both directions. Now what we've done is we've taken the information from the problem, we've written an equation of the line, and we've graphed it. And then we want to go back as a double check and we want to say, this point 1, 1 is supposed to be on the line. That was given to me. So let's go back and see if it is on the line. 1, 1. It is on the line. But notice, and it is one of the dots I used to draw the line, but notice that I didn't plot this here because it was given to me in the problem. I plotted this because I went to the y-intercept and went down 2 over 1. So this is a good check actually, because this was, I got this point by using rise over run from the y-intercept, and it also happens to agree with the fact that I know that this line must go through that point. So we have lots of different equations of lines, right? And they're used in different situations. We have what's called the standard form of the equation of a line. It's obviously true for all lines, but it's just not so easy to graph. And then we have the point slope form, which is really easy to write and also really easy to graph. So we've done some problems like that. And now we have the point slope form, which we use when we have the point, any point on the line, and also the slope. And what you end up finding is that no matter what happens, you end up getting it into this form because it's the easiest way to graph these things. So make sure you understand this. Follow me to the next lesson. We're going to get some more practice with the point slope form, and then we'll get lots of practice with writing equations of lines.